Welcome back, everybody, to another week for 113. Give me a quick yes, no over in chat just to make sure you can hear me. Evidently, you can see me because I can see that already. Okay, cool. Looks like pretty much everybody can hear me. So if you were one of the no's, then check your stuff because that's not me. So, hey, how convenient. The music happened to die right around there. Let's see if I can turn it off at exactly the same time. And come on, YouTube. You can do it. I promise. There we go. All right, so our topic for today, we are finally leaving CSTRs, which is to say that we're not going to talk about them in the middle of class anymore, but you will end up needing them on your second part of the project. So you just turned in the first part. We've got a little bit of a breather space here right now before the next part of the project and before any new homeworks come out. There is a short homework that's been posted. Remember, I sent out an email about that, bumping it back by a day. So there's a little bit more breathing room for the homework that's been posted right now. That one wraps up what we had finished with CSTRs last week. So some of the special cases, right? Gas flows and multiple steady states and that sort of thing. But there's only 3 problems on there, so quite a bit shorter than the usual ones. And that's to give us a little bit of time between this topic and the upcoming topic with the new reactors. What we're going to do today is talk about how to solve what are called ordinary differential equations. So there'll be an ever so slightly brief review of stuff that you probably would have learned in one of your calculus classes. Just generally speaking, the reason why we have divided it in the way that we have was because we learned initially the equilibrium reactors, and then we learned CSTRs. And the ones coming up next are 2 types of reactors that are classified as tubular reactors, which are the PFR and the PBR. To a lesser extent, we'll have a little bit of time, but we'll get to the batch as well. So these, the governing equations that are in the last few reactors, those are all ordinary differential equations. And that's to distinguish them from the first 2 reactors, the equilibrium reactor and the CSTR. All of these were algebraic expressions, right? So there were never any differentials or integrals or anything that we had to figure out for the first 2 sets of reactors, the equilibrium reactor and the CSTR. And as you can see, there's still tons to talk about even without differential equations. But starting on Wednesday, we're going to move on to these new types of reactors, and those will require a new type of solution. If we're lucky, we can still solve them by hand. But most of the time, we will not be able to solve these by hand. And so we'll have to come up with a different tool. And that's the point of today's lecture. And it's also the point of chapter 6 in your book. So all of this is covered in chapter 6 in your book. It's basically a review of, actually, there's almost no review of calculus. I assume that you still remember most of that. The new stuff is what chapter 6 is about, and we'll get to that in a minute. So what do we mean by an ordinary differential equation, at least a working equation? Usually what you'll think of when you see an ordinary differential equation will be an expression that looks something like this. So you'll have a differential like dn dv. I'm going to use n for most of the examples in here because that's what most of your differentials will look like, but it could be any independent and dependent variable. And then that will always be equal to some big function of stuff. So I'm just making up an example for this one, maybe 0.6 minus 1.1 times n. That will end up being a common kind of form for like a reversible reaction. So this term over here is generally going to be a function of n and v. And actually, I'm going to write it as v and n. And I'm putting those caps on there to remind us that this is going to be a volume, so not a volumetric flow rate. This term over here, it goes by different names, but generally you would just call it your derivative. sometimes it's called a differential. And then the thing altogether is missing one part. And the part that it's missing is an initial condition. So we always know something about the value of our independent variables at some point in the dependent variable. And so often that's written as something like n sub 0, which corresponds to n at v is equal to 0. And it's equal to some value, right? It'll just be a number, like 1, usually something like 1 mole per second or 20 moles per second or whatever it happens to be. Only when you put all of this together, this whole thing is what we classify as an ODE. So you haven't, quote unquote, written an ODE until you've got the derivative that's equal to a function and you've defined its initial condition. And we're going to see that eventually we have to solve a lot of these simultaneously. And so it's useful to know when you have written the equations that you need, which would be when you have these components that are stuck on it. This little thing, I said it, but I didn't write it. This is your initial condition. It doesn't have to be at v is equal to 0, but it nearly always is. We will see actually a difference later on where it's not at 0, but it's such a special case that it requires its own solution method. So what are those solution methods? Well, again, the one that I'm not going to go over in too much detail is what we would call the exact solution. And you obtain the exact solution, at least for all of the ODEs that we're going to see, by something called separation of variables. Any ODE that can be solved by the technique of separation of variables is called a separable ODE, because we're clever in the way that we name something like that. And that's, the separable ODE is the one that you would have learned about in a differential equations class, probably first. And so if we take that ODE above and we wanted to solve it by separation of variables, we take everything that has to do with n and put it on the side with dn, and everything else, presumably with the v, goes on the other side. So if we move everything with n over to the left-hand side, we'll have 0.6 minus 1.1n. And we'll set that equal to everything else, which is, in this case, just d sub v, or sorry, dv. So separation of variables says I can now integrate this, right? And now I just integrate the left-hand side and I integrate the right-hand side. And the result is whatever the solution needs to be. And so the boundary conditions go on the top part. So we start at the boundary conditions go on the limits of the integral, not the top part. So when v is equal to 0, we know that n sub n is equal to 1 because that's our initial condition. We can point that out. So our initial condition set these two on the bottom, and then we just integrate up to some unknown value, right? We don't know what n is and we don't know what v is. We just go up to whatever that value happens to be. The mathematicians do not like this particular form because it can get a little bit sloppy. So occasionally in a math textbook, you will see that the value inside the variable inside the integrand, the thing you're integrating with respect to, is not strictly the same as the thing that shows up inside of the limit on your integral, right? These two cannot technically be exactly the same thing. Every once in a while, you'll see somebody goes through and they want to be clever, or they are a mathematician, and they put like a prime or something on their variable of integration. But I will assume that you understand what I mean when I say integrate both of these with respect to n and then use n as one of the boundaries. The result of something like this will be more or less what you would think it would be if you work out each of those integrals. So n, to remind us, is a function of v. I've put with v in parentheses there, will be 0.6 plus 0.5 times the exponential of minus 1.1 times v. And then all of that divided by 1.1. 1.1. So the way that I went about doing that, you can check some very common forms for these for these integrals in Appendix A. So I've given you a lot of the most common ones that will show up. They probably won't get too much more difficult than what we've got here, right? This type of an integral, that's about as complex as we get for the most part. If it's more complex than that, there may be an exact solution available for it, but it might be more headache than it's worth to actually go about solving it. But that's perfectly possible, right? A fair number of these will come up with our reactor design. Again, keep in mind that separation of variables means that this side is a function of n only, and this side is a function of v only. And any number of constants, right? You can have lots and lots of v's or anything like that. The problem comes when you can't do something like this. So we often need a way to make progress on a problem, even if we can't solve it exactly. And we do have a way to do that. It's actually a really clever way to do it. I'm glad somebody came up with it and I didn't have to. The other option is to do what we call a numerical approximation. So this is the thing that chapter 6 is dedicated to, is how do we do a numerical approximation. You don't have to actually do a numerical approximation in any of your solutions. That's what we have Matlab for. But it's really hard to understand what Matlab is doing if you don't have, if we don't just open that black box a little bit, right, to figure out what is a numerical approximation doing. So a numerical approximation is a way of guessing what the slope of a function is, and then using that to predict what the new value should be. And we'll define all of that in a minute. But let's say that we didn't, or that we did somehow know, yes, we do a lot of great approximations. Say somehow the function n of v existed. That's a pretty good guess that the function n of v will exist. And we wanted to know what the value of the slope is of n of v between this point and this point, right? So try and straighten up our lines here. And we've just picked a random chunk of the n of v curve, right? We haven't really defined it as too much, but the distance that we chose to step, delta v, is from here to here. So the volume that we've got over here is v. By the time we get to this next one, we've now gone up to a volume of v plus delta v, right? We've just moved a little bit. Now, the way that we approximate the slope here between those 2 points, that's where there's lots of variations to it. So you can make this expression sort of as complicated as you want or as simple as you want. MATLAB's got some pretty complicated ones. We are not MATLAB. I cannot do this for a terribly complicated one. So I'm going to assume that that slope is a straight line. Right, so when that slope is a straight line, remember that slope is the derivative, right? If we were allowed to allow this delta v to get infinitely small, then the slope becomes the derivative at that point. So if we want to approximate dn dv over the region that we're interested in, we can say this is approximately equal to the rise over the run for the little chunk that we've described here, right? That's the definition of slope. It's rise over run. So the rise that we've got is the value of n here. So this is the value of n evaluated at v versus this point down here, which is n of v plus delta v. So our rise is the second point minus the first point. So that's n of v plus delta v minus n of the first point, which is n of v, divided by quote unquote the run, which is how far in the x component we went, which for our system is just defined as delta v, right? Because that's how far we went. And that expression ought to look somewhat familiar to you, like maybe hauntingly familiar to you. This is the expression where if you were to take the limit of that expression as delta v goes to 0, you have now exactly defined dn dv. But because we are approximating this, we will call this the slope evaluated at v. So the slope at v is estimated as the rise over run as defined here. that's not required, right? You could rearrange all of this and say, well, I want that to be the slope at v plus delta v. You could do that. Is it always assumed the slope is linear for this class? Nope, but you'll never have to calculate what the slope is. So we're only assuming that it's linear if I want to do this by hand. My guess is you won't do this by hand more than like once, which is now, which is fine. You're allowed to do that. So this term here, another way to interpret this expression is if I am starting off at the left point, right? If I'm starting off over here, that's sort of like the old point, and I would like to know, how do I predict what the value will be at the new point, right? If I want to come out to here, can I use the slope to kind of estimate the trajectory that I'm going to go, and then sort of step myself along a little bit? And so this one is sort of considered the new value of n, and this is considered the old value of n. Old in the sense that you probably already knew what it was. New in the sense of it has now gone a little bit beyond where we were before. So it's new in that sense. This was what we call our step size. And so we can, this term over here was our slope. So we can somewhat rearrange this equation and rewrite it as n new, the new value of n, is equal to the old value of n plus the size of the step that we took times the value of the slope, right? And the value of the slope is whatever dn dv happened to be evaluated at v. That bar that I draw there, the vertical bar with the v on the bottom, that means evaluated at. So dn dv with a big bar and a subscript v after the bar means evaluate the slope at point v. This term, so here again is step, slope, this is old, and this is equal to new. Right, and that is what we call a numerical approximation, right? We have guessed that a value of n that is quote unquote new, right, further out on the curve can be approximated if we know only something about the old stuff, right? The things that we already have knowledge about, which would be n sub old, and evaluating the slope at whatever the v portion happens to be. Yep, classic rise over run slope kind of equation. So we can use this to approximate the derivative, or sorry, the solution to our differential equation, because we can now write dn dv is equal to 0.6 minus 1.1 times n, where n0 is equal to 1. This is a function of just n, but really it could be anything. It could be a function of n and v, or just n. It doesn't really matter. But we can set up a nice little table here to see how this works. And the great thing is it's like a little, like those jack-in-the-box cranks, right? Where you just kind of put in the initial guess, and then you crank the wheel and let the algorithm tell you what the output ought to be. And it's like a little bit tedious, but the fact that we can get such really good approximations with such a simple approach is kind of nice. I mean, there's no reason you couldn't do all of the homework problems in Excel. You could totally knock them out with Excel. You would probably just get really tired of it. So we're going to take steps. The size of the step will be delta v. And so as we go, we'll keep track of which v we're at, right? We'll move along the value of v a little bit. We'll keep track of the old value of n. We'll evaluate this function, f of n old, right? That is going to be equal to 0.6. I'm going to have to make this a little bit smaller. So f of n is 0.6 minus 1.1 n sub old. And that is because we wrote it here, right? That's our f sub n that we've got. And then we can calculate a new value, n sub n, or sorry, n new is n old plus delta v times f. And we can set this up and go as far as we want. It doesn't really matter. I mean, it does matter. You have to have a stopping point sooner or later, but we don't really have step size. The tricky part is how do you get started, right? On the sort of 0th step, we don't care what the step size was. We are starting at a volume of 0, right? That's our initial condition. We don't have an old value, so we don't have to evaluate f sub n. And the quote unquote new value is just whatever our initial condition happened to be. So that's the only weird part of this approach. This is the first row is your initial condition. So we always start from your initial condition. There's very little math that you need to do in this case. So now you take another step, right? We go to our first step. We're going to let our step size here, this is always going to be equal to 0.1. Why? Because I like 0.1. It's an easy number to keep track of. If I have stepped to 0.1 and I started at 0, I have gone a total distance of 0.1. The value of the old function, or sorry, the value of the old n that I've got here is just equal to this value, right? That's what I knew before. And so I just kind of move that value over and I put 1 right here. I then evaluate my function, right? My f of n. So 0.6 minus 1.1 times 1. If I do that math, I will end up with minus 0.5. And now I can calculate a new value of n based on knowing nothing except the old value of n, which is here, and the value of my function, which is actually my slope, which goes here, right? I multiply that by my step size, and I've got a new approximation. So this looks like 1 plus the step size is 0.1 times the value of f, which is minus 0.5. And I end up with 0.95. And now I can just kind of like tick, 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 just keep going, right? I can just have this algorithm keep printing out values, increment the step. I don't change the size of the step, right? So I always go 0.1, but now I've gone a little bit further. So now I'm actually out at 0.2, right? The increment between steps is always going to be 0.1, but the actual value of v will be 0.1 and then 0.2 and 0.3 and 0.4, et cetera, et cetera. The reason that n old is 1 is because that was our initial condition. So this one just comes right down here. That's kind of the pattern that this will be, right? This will always end up being right down here. They will always follow one after the other. So now I'm going to take this value of 0.95, this one, and I'm going to put it right here. Because that's now my old value, right? The previously calculated value was 0.95. And now I take these, plug them into my function. So 0.6 minus 1.1 times 0.95. The result is minus 0.445. Getting a little cramped over here, but we can keep going. And the new value is the old value, 0.95, plus the step size times the slope, which is minus 0.445. And if I add those together, I end up with 0.906. And I can do, I mean, if you know Excel and you know how to do the little drop-down equations, you can write one row of this and then just drag the whole row all the way down and just keep going, right? I can take these out to whatever value I want, however many of these I want. I'm not going to do all of these. I did them elsewhere just so that you could see them. If I were to go all the way out to step 20, even all the way out at step 20, the size of the step has not changed, right? I have fixed that at 0.1, but now I've taken 20 steps of size 0.1. And so the volume that I end up with way out there, the V is 2.0. The part that you're not going to see is how I calculated 0.595, because I don't want to go through 20 steps of this. It would get really tedious. But the approach in terms of setting up the math is all the same, right? And then I'm left with 0.055 for the function. And then the new value is just equal to the old value, which is 595 plus 0.1 times 0.055. Oh, sorry, I think there's supposed to be a negative sign. Because this is 0.6 minus that. There's supposed to be a negative sign sitting in there. Let's get that out of there. Minus 0.055. And if we evaluate that, we have 0.589. We could have gone on, right? There's no reason that we have to stop at 20 other than I don't know, convenience. Maybe somebody asked us to go out to 20 steps, which corresponds to a volume of 2. But the key idea that we've got here is that we don't have a function, right? The analytic expression, or the exact solution, that gave us n as a function of v. The exact solution is the one that we did a couple of minutes ago, right? So the exact solution is here. So we don't need to know, or sorry, with that exact solution, we can calculate the value of n at any value of v, right? Plug in a value of v and it'll tell you what n ought to be. Even weird numbers, right? You could throw in a negative v if you wanted to and calculate it, but that makes no sense. So we would not use a negative v, but we can just plug in a value of v and get anything that we want. That's not the case with numerical approximation, right? We only have pairs. So we only know that when v is 0, the new value of n, or the value of n is 1. We know that when v is 0.1, the value of n is 0.95. When it's 0.2, the value is 0.906. When it's 20 steps later and 2.0, we know the value of n is 0.589. So the approximate solution, the numerical approximation, does not give us a function, right? The thing that the numerical approximation gives us is pairs. Those pairs are some value of the volume, v, and the corresponding value of n. And that's all we know, right? We don't know, there's no function that comes out from this. It's just a list of numbers. But that list of numbers is really powerful. We can find out what trends are inside of that list. We can always just look to the end of the list and find out what the value was at the end of the list. If we need to, we can fit that function to that data set to a function in order to use it. But there's plenty that we can do with just that list of numbers that we would suffice to call this the solution. So if you're asking for what is the solution to the problem, it is probably either the pair of numbers, or if you can get an exact form for it. Either one of those are considered interchangeably the solution to our differential equation. It might not be the solution to the problem, right? Maybe in the problem you're asked for, I don't know, conversion or temperature or something like that. But the solution to the differential equation is either this analytical function that you can get if you can do the calculus, or if you're doing a numerical approximation, you just get a list of values. So this is the form that Matlab takes. And so we need to know how Matlab is interpreting these. The form that's over here is going to come out as a big vector. And it's going to be exactly this vector. We're going to call that vector vsol. We don't have to call it vsol. We can call it anything we want. We can call it qbert if you want to. But I'm going to use vsol because that's what I use inside of the book. These values over here, and technically including this one as well. My vector over there is a little bit janky, are nsol. Right, and what we mean by nsol is these are the solution points for n. Matlab will connect the two of these. So Matlab is the link that we have between the two of these, and that's what we're going to rely on. We're going to let Matlab come up with these two vectors of information so that we don't have to do it ourselves, right? So that we don't have to fire up Excel and try to do this approximation all on our own. Would a question ask to list one or a couple of pairs? Usually it just asks for a single value, like the last one, because you can't, it's really hard. The last one depends on the previous one, depends on the previous one, previous one. So the odds of you getting the last number correct, having screwed up all the other ones, is basically 0. So usually the request will be, tell me the last one, or equally common is plot. Right, we can ask you to plot what these look like, and those are called profiles, and that's defined in your textbook. So might as well define it right now. A profile of n is simply plot vsol nsol. Right, and this will be what we call a profile. And that probably comes up every bit as often. We will ask for a single number as we ask for a profile. You can usually learn very interesting things in profiles that aren't immediately apparent. For example, the temperature can spike in the middle of the reactor and come back down. And so if you looked way out at the end of your reactor and you only looked at that particular value, you would have no idea that the temperature spiked by like 200 degrees in the middle of your reactor, which would be a problem. That's not a good thing. So our goal then for the next like 15 minutes or so, probably only 10, is how do we tell Matlab to give us this output? The key idea with Matlab is that the only thing that it needs to know is the starting row. Well, the starting row and one other thing, right? All I need to do is tell it this row. I love playing with this. I love drawing that. Give it that first row and tell it what this function is, right? If Matlab knows those two things, it will tell you everything else you need to know. So that's what we have to do in terms of getting our syntax into Matlab, is find out what the syntax is to tell it what that first row is, and then find out what the syntax is to let it have that function available as it needs it. So that's what we're going to do. We're going to do this exact example, but we're going to put it into Matlab. So if you've got Matlab open, follow along. But if you don't worry, I will post these. And they also follow very, very closely to what was in the book, because you happen to be talking to the person who wrote the book. It's so funny. So I can make sure that they line up pretty well. So let's open up Matlab. Here's our Matlab. I will show you the profile of n is just the plot of v versus n. So the general approach starts with the solution that we want. So we kind of write this line, and then you can kind of build up and you can build down afterwards. The thing that Matlab is going to provide us is those two vectors, right? So we're going to get a vector of vsol and nsol. So a vector of volume points and a corresponding vector of n points, right? And they're both going to come out as column vectors, and we're going to get both at the same time. We're going to get them from a function called ODE 4.5. ODE stands for ordinary differential equation. 4.5 is the approximation that it's using in order to make its estimates. It is insanely more accurate than the one that I just showed you. It also doesn't take the same step size. It will refine it as needed. So it gives excellent results for everything that we're worried about. The system of inputting values to ODE 4.5, it has three parts to it. The first part is, what's the function I'm going to use? That part looks really similar to what we saw with fsolve, right? fsolve needed to know what was the function that I was going to try to solve. Similarly, ODE 4.5 needs to know what's my function. And so the function here is the derivative function, right? The f of n that I had said before, but we'll define that in a moment. It also needs to know, how far do you want me to take this solution? Remember I said in the notes, we started at 0 and we went out to 20 steps where we were at a v of 2. We could have done anything that we wanted, right? We didn't have to go out to there. But just to keep it the same, we're going to say, yes, please, again, go from 0 to 2. Because that's how far we took the volume last time, right? We went from 0 out to 2. And then the other thing that it needs is the initial condition. So we just say, what's the very first value of n at the corresponding value of 0? That is 1, right? So if we wanted to do this, this is your function. 0 goes up to v max, and then your initial condition. Initial condition. So those are your inputs that you require to ODE 4.5. And if you do those, it will output everything else that you need, right? It will now solve it. So we don't have anything else to solve for this. Occasionally you'll see it written a little bit differently in terms of actually defining the volume up at the top and then you passing it as an input argument, which is perfectly fine. It's up to you. But this is the only line that we need in order to do all of the math that we just did in that big table. The only other thing we need to do is define the function. And so that will look like a local function like we've seen before. The starting line of this always looks like what we have right here. So the output will always be dn dv, and it will always be a function of the independent variable followed by the dependent variable, always. Even if we don't need the V still has to be there. It always has to be included, right? Even if you don't need the value of V in the actual function, it still has to be included. That's just part of the syntax behind it. If n is not defined at v is equal to 0, then you have a problem, right? Generally, it doesn't need to be 0 here, but you need to know the value of n at some value of v. In other words, you need to know an initial condition. So the pairing of this 0 and this 1 is the initial condition. It doesn't have to be at 0, but they're all going to be at 0. If you don't know what it is at 0, you need to know it somewhere else, and then you're probably not doing a reactor. There's only one special type of reactor that you don't know it at 0, and we'll spend an entire lecture dealing with that one reactor. So for the most part, we will always know its value at 0. The output that we have here is our function, right? So this is 0.6 minus 1.1 times n. Right, that was the function. If you look back to the notes that we just had a moment ago, that was pretty much the only thing we were actually doing that was calculating anything. We were using our approximation, our numerical approximation, saying that I think if I know what the value is here and I want to know what it is out here, I can assume it follows a straight line between the two. That was part of the approximation, right? That part of saying here's where I am and here's where I want to get to go. That is the thing that ODE 4.5 is doing. So we never have to tell it like, yeah, assume that this is a straight line or something like that. ODE 4.5 is going to make those approximations very, very accurately. If we then wanted to plot, for example, the profile, we would say that it's VSOL, NSOL. Make sure we get something like that. And this is it, right? This is, make sure I save this. Example 1. That is how we would solve this thing numerically. That is actually, to me, a lot easier than, well, I don't want to say it's easier yet. Once you get used to the syntax to it, you'll notice that we always come back to this exact form and then just kind of tweak it a little bit, right? Maybe the function gets a lot more complicated. It'll get a lot more complicated. And maybe there's more than one, but we'll get to the more than one in a moment. So let's go ahead and plot that, and I will dock this thing so we can see it. There's our function. Right, so this is our profile of n. And so if we want to know what the value of n is way out here at the end, and we put a tag up there, I don't know if you can see the tag or not, but it says it's 0.5958. If you wanted to know that for the, without being able to see the tag, if you just ask Matlab to tell you what's the last value of n that you calculated, it'll tell you it's 0.5958. That is basically spot on what we would have seen with the other approximation. It's just the other approximation is not quite as accurate in here. There's a question in chat, what's independent and what's dependent? The independent variable is always the one that appears in the denominator. Anything that appears in the numerator of your differential, those are always dependent variables. So in this case, n is what shows up in the numerator, so it's dependent. Whatever shows up in the denominator is called your independent variable. We can compare this to the exact solution if we wanted to. So if we said, there's no v in the function. There is a v in the function. So that's the tricky part is, yes, there is no v. And in fact, Matlab is actually complaining to me. It's saying you didn't use the v. This is the syntax. You have to include the v in there just so that Matlab knows which one is which, even if you don't end up using the v in the actual derivative. But the v does show up here, right? It's in the denominator. It's just we never have to actually calculate it because Matlab is going to do it. So we can also compare this to our exact value or our exact solution. So if we want to plot this, say from 0 to 2, we can say plot v plot. And then if you look back to the previous written notes, you'll see that the exact solution was 0.6 plus 0.5 times the exponential of minus 1.1 times v. And then all of that divided by 1.1. And if we compare the two of those, not surprisingly, MATLAB's differential equation solver gets the exact solution very, 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 very closely. Pretty much spot on, right? For all intents and purposes, it's exactly the same thing. You could look out probably 9 or 10 decimal points and you would see no change whatsoever. And so the point of showing the exact solution on top of the numerical approximation is that I want you to have confidence that ODE 4.5 is doing a really good job. So first we had plotted the approximation and then we plotted exact on top of it. So legends always help, right? If you have more than one component on there, you should always throw a legend on there. And that's that, right? So that syntax that we've got here is covered in your book, but you're going to get used to it after a while because in the same way that we've used fsolve for basically any equilibrium reactor or any CSTR that we could not solve by hand, we will be using ODE 4.5 to solve basically any tubular reactor or batch reactor that we cannot integrate by hand. And the class of things that we can integrate by hand is probably even smaller than the class of things that we can algebraically solve by hand. So it's going to come up pretty soon. I will go ahead and post this one, but I want to show you what happens if you have more than one variable, more than one independent variable, which is possible. And in fact, probable. We will get there sooner than you might want us to get there, but we will be there momentarily. So let's go back over here and look at a different class of differential equations. We got to draw a straight line. There we go. So this other class of differential equations are called coupled. Which is not as bad as it seems, but the syntax is weird. And so a coupled ODE has the following characteristic, right? You've got a differential equation where the independent variable is NA and the dependent variable is V. And maybe this one is going to be equal to a rate. And we're just going to define rate just so that you have an idea that this is not like a random example. It does actually look like a real example. And that rate can be a function of the other components, right? And so what we will end up seeing is that we also have to have a differential for those other ones. And so we have another differential equation, which will end up being an independent variable that's different, right? In this case, it's n sub b, but the dependent variable is the same. It's still the volume. This function will be a little bit different, right? This one, if you're making v, might be 0.1 Na minus nb. And don't worry about where those functions came from. That's the topic for the next like 5 lectures, is how to come up with that function. The part that I want to point out is that the ODE for NB contains within it n sub a, which itself is its own differential equation, right? The n sub a is its own independent variable, which is a function of volume, and it's got its own differential. Similarly, up here, if you look at DNA, DNA has within it the independent variable n sub b, and n sub b is itself its own differential equation. And so both of these would have to have their own initial conditions. So you'd have to know where Na0 is equal to something and where NB0 is equal to something. We're going to say it's equal to 0. Again, where those initial conditions come from and how that function is written, don't worry about that part yet, because we're going to get there, right? That's the topic of basically all of the reactor design that we have after that, is how do we set those things up. But the key point is this sort of crossing that you see in the middle. The result of one of the differentials depends on the solution of the other differential, and that differential itself depends on the other one. And so this set of differentials is what we call coupled, because you can't solve for one of them without solving for the other one simultaneously, right? It's not at all different than having 2 equations with 2 unknowns. It's just here you have 2 differential equations with 2 unknowns, the unknowns being the independent variables. This has, there is no problem at all for MATLAB solving these. For you to solve them, there's like 2 that we can solve by hand. And I'm not talking like that I will ever ask you to solve. I mean, there's like 2 anywhere that anybody can solve. It's very difficult to solve a set of coupled differential equations by hand. There are very, very few that we can do. The way that we'll go about doing this is to basically lump everything into a single variable, and that variable will itself be a vector. So that vector by convention is just called y. That is not a variable for like a reactor or something. It's just used to assemble differential equations. So it has no physical meaning, but it carries along all of our other stuff. So the vector y will contain NA and NB. Similarly, the vector of initial conditions, y sub 0, will contain the initial conditions for everything else. So NA0 and NB0. And then similarly, we can define sort of a vector of differential equations, dy dv, as this column vector of each of our differentials, dna dv and dnb dv, or as many as we want, right? We will probably get to a point where we will solve 6 or 7 of these all at once, maybe 8, I don't know. Wait, John, what was that trick? Oh, right, if you draw out here. Yeah, there it was. Thanks, John. I remember your trick. So this is what we would provide to MATLAB, right? We would provide it a series of vectors like this. And the output that MATLAB provides, or ODE 45, will look like this, right? We will get 2 outputs. We will get VSOL and YSOL. And this will be equal to ODE 45 of a bunch of stuff. If you want to know what the stuff is in here, this is what's being given in chapter 6. So you'll have to look that up. We'll do a couple of examples in class on subsequent days, but you should acquaint yourself with chapter 6 for something like this because it's going to be important. So the VSOL that we get is going to look like a vector, right? And it's going to start at our initial value of V, and it's going to go up to whatever the last value is. Could you solve this with eigenvalues and eigenvectors? That's actually what ODE 45 is doing. Well, I shouldn't say ODE 45 is doing that. If you open it up, it'll just look like a bunch of, I don't know, for loops and stuff like that we've been accustomed to. The approximation that's being used by ODE 45 has its origin in eigenvalues and eigenvectors. The YSOL will be a matrix. Yeah, this is the first time we actually need a real honest to goodness matrix. There's no way to fudge it with a couple of vectors. We will always get a matrix coming out. And that matrix will contain 2 columns. The first column will be our values of n sub a all the way out to whatever its last value happens to be. The second column, let's make this blue so that you don't confuse the 2. N sub A. The second column will be N sub B, right? So that'll start wherever you were with your initial conditions, which is of 0, and it'll go out to whatever the last value happens to be. I say last because we don't know what the value is until we actually solve the thing. So it's hard to tell what the last value would be. But notice that they're paired, right? The first value of V still corresponds to the first 2 values of NA and NB. So if we needed to make a plot, we could still do that, right? We have a corresponding value of V for a corresponding value of N, no matter which one we're looking at, right? They still work like something like that. If we wanted to extract those values, we could do so with a command like NA is YSOL of all rows, column 1, right? Because it's a column vector, and it's the first row, or sorry, it's the first column of the matrix YSOL. Similarly, N sub V is YSOL of all rows, column 2. So if we wanted to make plots or something like that, we could do so, or analyze output values or something like that. So this structure, we're at 350. I don't want to go any further than that. This structure is the one that's covered in chapter 6. The ones that you need to particularly pay attention to, I mean, they're all important. It just won't work if you don't do it right. But usually the one that's tricky is dy dv. And so there's a couple of examples in your textbook that show you how to set these things up. There's more than a couple. We will eventually get to actual reactor problems where we have lots and lots of these. But please take a look at chapter 6 after you finish homework 3, because we're going to come back to this pretty routinely, because it's how we're going to end up solving all of our differential equations. So it's 3:51. I don't want to keep you anymore because I know some of you might have a class right after this. But as usual, I'll stick around. If you have any questions or anything like that, feel free to ask. We will throw some of our music back on, which if anybody plays any of the Final Fantasy series may be able to identify where this is from. Not that one, that was a random tone. This one. Yeah, anything in the numerator are the dependent variables. The one in the denominator is the independent variable. So, oh, I have my pen upside down. So any dx dy, this one is your independent variable. This one is your dependent variable. Did I not write that somewhere else correctly? Oh, yeah, right there. Fix that. These are your dependent variables. Right, and then in this expression, it's the v over here. This one is your independent variable. I can't write with it. Excel? It's a good question. For my own personal use, I probably use Matlab more. If I had it my way, I would overhaul our entire curriculum so that we do not use anything except Excel in all of our classes. But that's never going to happen. So. And personally, I like Matlab. So. The due date still says today at 11. Let's fix that. You're referring to the due date for the quiz? Okay, let's take a look. partial pressure of PI the initial or the final PI? It's the partial pressure inside the reactor. If you're referring to the rate that's being given, the partial pressures that you see inside that rate, those are the partial pressures inside the reactor. You're welcome. It's pretty quiet in here, so we're going to go ahead and wrap this up. Let's go ahead and stop sharing, or sorry, stop recording.